In the previous video lecture, we saw some laws of large numbers, which means that for a sequence of random variables, their partial sums given by Sn equals x1 plus xn satisfy this convergence. And this convergence can be in probability. If it's a weak law of large numbers, it can be almost sure, and then we call it strong law of large numbers. And then we saw two versions of laws of large numbers. One by Chebyshev, which assumes only that the variances are bounded and that the covariances, 2 by 2 covariances, is 0 for I different, for I and j different, which is a much weaker than assuming xi and xj are independent, and this is much weaker than assuming all the xn's are independent among themselves. Then this was Chebyshev's weak law of large numbers. And then we saw a strong law of large numbers, assuming that the expectation of xn are all bounded by a certain number that does not depend on n to the fourth moment, and assuming that these random variables are all independent, or at least that each group of 4 of them would be independent. But let's say assuming the xn of this sequence of random variables to be independent. And now we're going to see a much stronger theorem, but which has also, which is a stronger, which is also a strong law of large numbers. It has more requirements. It requires that they not only are independent, but they have the same distribution. On the other hand, they do not require fourth moment. They do not require first moment, second moment. They only require first moment. And this is known as Kolmogorov's strong law of large numbers. And in Kolmogorov's version, these random variables had to be all independent, but there is a more modern version of the theorem that was proved rather recently in 1981, where you only need them to be pairwise independent. So what is it? Well, we have a sequence of random variables. We're assuming each pair of these random variables is independent. And we assume that these random variables all have the same distribution. So this is stronger than the two law of large numbers we saw before. And we assume they are integrable. They have finite first moment. Their expectation is a finite number. And the theorem says it satisfies the strong law of large numbers. In this module, we're going to omit the proof of this theorem. It is quite complicated and involved. There is a reference in the lecture notes for those who are interested in going through the proof. We're not going to see it in the video lectures. It's not in the lecture notes and it's not examinable. We just want to emphasize the following, is that this is the ultimate law of large numbers. We cannot have laws of large numbers with any less assumptions than these ones. These ones meaning integrable random variables. And what do I mean by this? I mean, if the random variables xn are independent and identically distributed, then we cannot have any convergence of Sn over n converge to something unless x1 is integrable. And if x1 is integrable, because they all have the same distribution, is identically distributed, they are all integrable, of course. And how can I make this precise? Well, I'm saying if the random variables are IID, then the fact that their sum will converge almost surely to a certain number, mu, or even in probability, is equivalent to it being integrable. They have to be integrable, and this is what the following proposition shows. The proposition says if xn are IID but not integrable, then this does not converge to any real number. Not only it does not converge to any real number, this sequence of averages of xn's, if we plot the graph of this, n, and here Sn over n, is not that it does not converge because it's oscillating like this. It does not converge because the lim sup as n tends to infinity of Sn over n equals infinity. So either this sequence is going bigger and bigger in both directions, or at least in one of the directions. So let us end this first part of this video lecture with this discussion that we had about this proposition and about Kolmogorov's strong law of large numbers. And for the next part of this video lecture, we will prove this proposition.